Yeah, I'll send you in a couple of hours the study guide and the practice exams for the exam on Monday. So I'll finish working on it after we are done with today's class. Um, okay, so let me check what the lecture is today. Um, Today is lecture 20. Oops. Okay, so just as a brief reminder of what we were discussing last time near the end of class, let me see if I can find some animations. Oh yeah, so let's do this one. Let me show you this. So okay, so we were talking about the integral. So the integral is again a very different concept from the derivative because the derivative has to do with the slope of the tangent line. For an integral, what you have is a curve, like in this, I don't know if everyone can see the animation, right? So here you have like a function of x, like in this animation is x squared minus 1. And so the integral, what it does, like an integral from a to b, which is what you see here. So here a equals 0 and b equals 2. So that's why it says the integral from 0 to 2. That integral is just like the area between the curve and the x-axis. But if you remember what I mentioned yesterday, the area, I mean, it's in quotes because whenever the curve is under the x-axis, this area contributes negatively. So it is like kind of like in this case, like it would be like the green stuff, like the area of the green stuff minus the area of the red stuff. So it kind of comes like already it comes with the sign. Okay. So if you vary the bounds, like which is what's happening here, if you vary the bounds, like the area could get like there could be more area in this case, but also you could vary the other bound, say from -2 to 2, and then like I mean, you can play a little bit with the with this animation, like or where you want to start the integral. You can also choose other like other functions. Okay, so in this case, for example, if you integrate this from -3 to 2, we'll see how to compute these values probably today, but you can show that this area. Oops, let me maybe put it here. Yeah, so you can compute, like you can see that this area, net area, that's actually what I should be saying. There's kind of more like area on beneath the x-axis and above the x-axis, like it's kind of clear in this picture. So that's why the integral comes out negative, because again, this area is all being counted negative. Okay. So it is, it is fine for an integral to be to give you a negative value. That just means that there's more stuff underneath the x-axis, and there's a it's also possible for the integral to give you 0, right? Which you see here, because that just means that there's as much stuff above the x-axis as there is below the x-axis in terms of area. Is that making sense? Intuitively, any questions about this so far? So again, like the integral can be positive, like that as a number. It can be positive, negative, or 0, because it's just like a competition between different areas, like those above the x-axis versus those below the x-axis. Is that making sense? Okay, now in practice, if you wanted to again like today, like the purpose is to kind of find these numbers, like these areas in a useful way. That's uses like the fundamental theorem of calculus. Like if you didn't do it that way, what you could do is try to do what I showed you last time. So like in the more like in a more like limit approach, what you would do is say, well, you don't know like how to find the area. I mean, you are trying to find the area under the curve. Like the curve could be weird. Like for example, this is like natural log of x plus 5 plus 4. I mean, we don't know like the specific formula for the area between this curve and the x-axis. But what you can do, let's use this approximation. Well, no, maybe this one will fine. But what you can do is kind of like, you do know how to find the areas of rectangles. So you can just like approximate the area under the curve by areas of rectangles, right? The height of the rectangle is given by the value of the function, okay? So like the idea is that as you make the rectangles thinner, right? As you make the rectangles thinner, you would expect this approximation of the area to be better and better and better and better to the actual area you care about, which is kind of what you're seeing here in the animation, right? So again, like it is kind of like a big process to define all of this. But you want to say that in the limit, as the width of the rectangles approaches 0, right? Because they're becoming super thin, as they're shrinking to like almost like a line, they always have some sort of like width to them. They're not lines, but as you make them smaller and thinner, these partial sums of areas or this partial approximate area should be equal to the actual area that you care about. Is that making sense? So like there's like the actual way to define the integral in terms of a limit is as the limit when you know the width of the rectangle equals to 0 of like these partial areas. It shows that doing it that way in practice, it is like a it's not too convenient to use if you actually care about the value for the integral. So finding the integral in this way is kind of complicated, and that's thankfully what we don't need to do because we can use the fundamental theorem of calculus. Okay, so let me show you what the idea is now. Let me see if I can go to GeoGebra. Okay, so let's say I give you like a curve like or a function like y equals x. Okay, integral x. Okay, so here you're going to so what I'm doing showing you here is kind of like I'm showing you like we're going to try to find the area between the function and the x-axis, right? Which is what you see here, but I'm going to be moving the endpoint. Okay, so like this, I'm going to find the area from 0 to a certain number, but where that certain number finishes, where the interval finishes, like the right endpoint of the interval, I'm going to let it slide. So think about it like kind of like a sweep out, where you see like these numbers are growing in size, right? And as you shift the endpoint, right? Like the value for the area, which is going to be the integral, will get bigger, right? Because you're moving everything to the right. So like what we are going to do is compute this area in the case where where the endpoint is kind of varying. So let me do that on the iPad to show you what I mean. So what I'm trying to say is that kind of since you are going to be moving the right endpoint, like the area is going to depend on the value of the right endpoint, so it's going to become a function. So like basically what I'm trying to do is kind of find a function from this integral. So let me start there. So I'm going to have like a function. Well, let's start with a concrete case of y equals x, which is what I was showing you. So I'm going to find the area between the curve and the x-axis from 0 to t. I'm going to find the area. What's this area? This area is, is that making sense? Because like again, this notation just means I want to find the area of this function from from starting at 0 and finishing at t. So this is like the this area is being represented by this symbol of the integral. Okay, but now what can anyone guess like what the area of this triangle? I mean, it is a triangle, right? So what's the area of this triangle? What's the area of the triangle? It's right. It's base, right? The base is t times height. The height is also t, so it's t times t over 2, right? So it's t squared over 2. Good, perfect. Good, good. So whenever you plug in your favorite value of t, you get the formula for the area, right? So if t had been 1, if t is 1, I believe it's what we had done before, right? If t is 1, I think we can, if we go back to our notes, well, I had done it for t equals 3, right? I had stopped like the integral at 3 last time. So that would be 3 square over 2, which is 9/2, and so that gives you the correct answer, right? The advantage of doing it this way is that it kind of you can plug in different values on where you want to finish the integral, doing the integral. So in this interpretation, it really depends on like the formula for the area depends on t, because you give me a value for t and I'll then know the number. So you can think of this as a function of t, okay? And so you can call it a of t, because that means like the area. So the area function, you can call this like the area function, since it depends on t. Is that making sense? So far, so good. And so now, like once you have the function, like kind of at some moment, like you could ask, well, how is this quantity, like how is this function actually related to the function? I mean, remember the function we started with was y equals x, right? How is this related to this, right? Is there like any relation between oops, between the the new function and the original function you started with, just to see if we can find something useful? Let's do another example so that you can see like a little bit of a pattern. So for let's say even something easier, imagine I had just given you the equation, like the function y equals 3. So here's y equals 3. So the function doesn't even depend on x, right? And I ask you to find the area from 0 to t, right? So here's 0, here's t, right? So like the area function in this case, the area function in this case is the integral from 0 to t of 3 dx. And this is just the area of a rectangle, right? So what's the area of this rectangle? Three t, good. 3t. So we can make a table. I mean, of course, I have done this many times, but like that can be enough to give you like essentially like some sort of pattern of what the relation is between the function and this like the associated area function. So here we have these two things. So we just saw that if the function is y equals x, right? The area function is t squared over 2. And if you right, and let me put this here, move this a little bit here. Oops, sorry. And if you put y equals 3, for example, the area function in terms of t is 3t. So anyone, I mean, if you had like I don't know, I mean, maybe some of you have seen it before, but do you see any sort of relation between the two columns? This is a function of t, right? So we could take a derivative with respect to t. What's the derivative of this with respect to t? What's the derivative of t squared over 2 with respect to t? It's just t, right? And what's the derivative of 3t with respect to t? It's just 3, correct? So is there any relation that you see between the first column and the second column? Sorry, the first column and the third column in this chart. Well, maybe this one is more clear to this one. I mean, maybe the second row is easier to see that they're related because you're getting the same number on both columns, right? So it's very clear that this is the same as this. Okay, but how about this one with this one? I mean, except for the fact that you're changing you're changing the name of the variable. It's kind of the same formula. It is like um t instead of x, it's just t, but it kind of like has the same format. It's just like this the variable itself. So this is not a coincidence. So that's basically what the fundamental theorem of calculus says. What the fundamental I'm about to write it, but what the fundamental theorem of calculus says is that the derivative of the area function is going to be the function that you started with, the function that you're computing the area for of. So let me write that down. This is kind of like the most important theorem of the entire course because it kind of gives you like a relation between these two concepts of the derivative and the integral. Then the derivative of the area function is f of t. So the area function is a function whose derivative is f of t. Okay, so I mean, again, it has a lot of consequences. It will give us a useful way to compute the areas, but let's just start for, I mean, kind of not clear where I should start. I'll start maybe telling you why this is true. It's a little bit technical, so it's fine if you don't, like, if the proof is kind of not fully digestible at this moment. But it's kind of useful to see it. So it's nice to just check, to have like a good idea that you are understanding the concepts to kind of go through it. And then after we go through the proof, I'll tell you how do you use this in practice to to compute the derivative. So to compute the integral. Okay. So let me give you an idea of the proof. So you want to find the derivative. So let's use the limit definition of the derivative. I'll use this one in terms of h. What is I don't know if anyone remembers this. What should I put here? A, like in the limit definition of derivative, what goes into the first slot? A of what's it? T of what? Exactly. F of t plus h minus f a. Yeah, exactly. Okay, but let's try to think about this geometrically on what that means, right? So what is, I mean, I'm not going, okay, I'll put proof in quotes because I may not go into all the details, but it's good to just understand what's happening here. So what is, again, what is A of t. Well, if you had like a function y equals f of x, then A of t, right? Here's t. So A of t is going to be all this area, right? Right, is that area from 0 to t. What is oops, let me see if I can copy. I just don't want to draw it again, so let me copy paste this picture. And this is convenient to do this too. What is A of t plus h, right? What is A of t plus h? Well, here's t plus h, right? And so let me lift this up. And A of t plus h is here, right? Is an area from 0 to t plus h. Uh, is that making sense? Are those two pictures kind of realistic? So we're comparing, we're subtracting from this area, we're subtracting this thing, right? So what do we get here? What happens when you subtract these two quantities? This minus this. Geometrically, what are you getting? Right. It should be like the portion between t and t plus h. T and t plus h, perfect. So like this portion. So let me copy paste this again, right? Okay. So right, the thing that survives, let's say kind of somewhere in here, maybe. So let's erase this, erase this. All right, so this is what's left, right, of the integral. I mean, once you take the difference between those two areas or integrals, this is what's left, right? And so this is, again, this is what we're calling, corresponds exactly to A of t plus h minus A of t. And, okay, now the idea is like, again, remember the philosophy of a limit. We're going to compute, we're interested in that quantity when as h approaches 0, right? We're interested in this quantity in this area as h approaches 0. So what does it mean for h to approach 0? It means that the distance between these 2 points, edges, is really, really small, right? So what that means is that, right, because that's very small, that should be well approximated by these rectangles that we were talking about before. Is that making sense? So they should be well approximated by the rectangles that we were talking about earlier. So let me draw them for you here. So like I have a rectangle kind of like in here. Right, I mean, there should, like, of course, there's a difference between these two quantities, but like in the limit, you would expect that to be fine. And it can be justified better because like the function is continuous and other things that, you don't have to worry about. Uh, okay. But so what would be the area of this rectangle? Well, the area of this rectangle, what would be the area? This has area equal to what? The width is h, right? Because it's the difference between these 2 points. So the width is h times the height. The height is like f of t. Is that making sense? So again, like my claim is that this is actually, if you wanted to go through all the details, you would do sort of like squeeze theorem because then this other, like you can also approximate it by a rectangle, which is a little bit bigger. So you kind of squeeze it in between two quantities. But I mean, like this is kind of like good enough for you to get like an idea of what's going on. So when you go back into this definition, uh, because there's a limit involved, what I'm trying to say is that it is essentially the same. I mean, once since you're taking limits, there won't be much of a difference between this ratio, this difference, and the approximate difference which I'm taking here, where it's like just h f of t. But the good thing, if you put it this way, is that the h's cancel, right? And so there's no more h, and this doesn't depend on h. So like the answer is just f of t. Okay. So that's why the derivative of this area function gives you f of t. Is that making sense? It is an elegant argument, takes a little bit of time to digest. It's okay if not all of it makes sense at once, but over time it becomes like, you know, uh, it becomes like, I think it will make more sense. But it's like a very cool argument, and it is like again, like it is really like the most important result in all of calculus one, probably in all of calculus, um, because it will give us a way to compute these integrals. So I'll tell you about that. Oh, let me check first if there are any questions. If not, I'll tell you about that like after a mini break because it is a little bit different where we are about to do next. So it's a good place to do a pause. So are there any questions before we pause? Okay, let's do a 5-6 minute break, and then when we come back, I'll start giving you the basic tools on how to compute this area formula with this information that we just had found. Okay, so let's uh, check back again about this in like 5 or 6 minutes. Okay, so resume. Let's use this to find values for integrals. Again, it will be surprisingly useful. I'll start with an example first, and then I'll tell you like the general method. But it's kind of nice to find like do it by hand before like moving to the full generality. Uh, and again, we'll spend like basically the remaining part of the course just doing this. So this will be like what we'll do for the remaining classes in the course. Let's see. So let's say you want to find the integral from 0 to 1 of x squared dx. What does that mean? It means that here you have y equals x squared, right? Here you have 0 and 1, and you want to find this area, right? Okay, but so what we're going to do first is instead of find so that's what this corresponds to. Okay, this quantity corresponds to this area here. But what we're going to do first instead is to find something which looks a little bit more general. So it's kind of weird. But so we're going to find instead is so instead of doing the integral from 0 to 1, I'm going to do the integral from 0 to t, and we're going to get this. Okay. So now this corresponds to this. But what the fundamental theorem of calculus says, so fundamental theorem of calculus says, well, the fundamental theorem says is that the derivative of this function, right? The derivative of this function is the function that you started with, just with a, a change of letters. So if it was, instead of being like the function x squared, it would just be t squared. But it's except for like a change of letters, it is the same function. Is that making sense? Are there any questions up to this point? Is that okay so far, so good? But then, okay, and then it is kind of like a weird problem question, but you are asking now, okay, I'm trying to find a function. I'm trying to find a function whose derivative with respect to t is t squared. So now you kind of have to think backwards because usually up to this point, we've always started with a function and took its derivative. Now we're going in the reverse. Like we're asking, well, I know that the derivative of the function is t squared. What should the function be, right? Um, so and here again, there's not like an obvious way to go about it. You just have to think, what could that possibility be? So what do you think should be, if you remember, what kind of function could have derivative t squared? What looks like something that could have derivative t squared? Yeah, t cubed over 3, right? So you here are like, well, so maybe, okay, so that one definitely works, right? But then the question is like, how do I know, right? How would I know that there are no other options, right? Could there, so the question, like, then the question becomes, could there be another option, right? Okay. And the idea is that, yes and no. Okay. Yes, in a very silly sense, because if you have a like, if you take a if you take something like t cube over 3 and add a constant to it, then you will still get the same derivative, right? Because the derivative of a constant is 0, but that's the only thing that could happen. So all the other options look like um, t cube over 3 plus a constant. So there's no other that would be important, but there's no other possibility. Like two basically because two derivatives that have the same two functions that have the same derivative differ by a constant. So this is like I don't think I mentioned that explicitly before, but let me say write it here. Since two functions with the same derivative, constant and most. Is that making sense? So far, so good. So what I'm saying is that if you take tq over 3 and add like a constant like +1, +2, -7, plus pi, they still continue to have the same derivative, which is t squared. But besides that, there's no other option. So a of t is going to be, a of t was the integral from 0 to t of x squared dx, and because of this, it's going to be t cubed over 3 plus a constant. Okay? Okay, so let me stop here to see if this is whether so far there are any questions about this. Are there any questions up to this point? But we also know something else, which is that a of 0. What is a of 0? Is the integral from 0 to 0 of x squared dx, right? What's the integral from 0 to 0 of x squared dx? What do you think that should be? Pictorially, just think about it as in terms of the picture. Is the area from 0 to 0, right? So what should the area from 0 to 0 be? And I mean, it's meant to be like a question, the most obvious thing you could think about. Yeah, good. It should be 0 because you have no chance to draw any areas, right? You get like a line or you get basically nothing, right? It has no area. But if you look at this formula, this would be, this should also be then like 0 cubed over 3 plus the constant. So that means that 0 equals 0 plus the value of the constant. So the constant actually had to be 0 in this case. So what that means is that that gives you the formula for a of t. So a of t, which was the integral from 0 to t of x squared dx, is actually t cubed over 3. So in this case, there was no need to add the constant. Is that making sense? So what is a of 1? A of 1 would be the integral from 0 to 1 of x squared dx, right? That's what a of 1 is because it's replacing t with 1. But if you look at the formula, it is 1 cubed over 3. And so this is 1/3. So that means that the area of the original parabola between 0 and 1 that we were trying to find, this area will be just 1/3. Is that okay? Is that making sense? Well, in this case, the constant, so what I was saying is that, like, first we were trying to find a function whose derivative was t squared, right? So one candidate was t cubed over 3. That works. But I'm just saying something else could have worked because, like, you could have had, like, t cubed over 3 plus 1, for example. That has also the same derivative, right? Or t cubed over 3 plus 5. So all of these are functions with the same derivative as t cubed over 3. Because if you remember the derivative of a constant is 0. Is that making sense so far? So a of t, and that's the only difference that can occur. So the words that, I mean, the most different that they can be, they can only differ by a constant. That's the worst thing that could have happened. So what I'm saying is that this thing, we know for a fact has to be t cubed over 3 plus some number, but I still don't know what that number is supposed to be, right? But if you plug it in at 0, you get the integral from 0 to 0, and that for sure is going to be 0. So that, if you use the second formula, it has to be 0 cubed over 3 plus this number. And so that forces this number to be 0, you see? Is that making sense? And that's why actually your first guess was the correct one, in the sense like like in this case, you didn't have to worry about this extra constant. Um, and so the answer had to be 1/3. I mean, once you know that the formula, the the area formula is t cubed over 3, and if you wanted the area up to 1, you just plug 1 here and then you get 1/3. Is that okay? No, good. But isn't that cool? I mean, it's like a very elegant way to find this out if you think about it, right? Let's try to, I mean, this is fun. So let's do one more as a warm up, and then I'll give you like, the actual method. Okay, so like here's another one. Imagine I had given you, just to make it easy, like huh, so imagine I had given you the function cosine of x, right? And I wanted to find the area between cosine of x and the interval 0 pi over 2. Okay, so the area that you see here. So I want to find, Oops. The area from 0 to pi over 2 of cosine of x dx. I want to know what this the value for this area is. So again, the trick, as I'm explaining it right now, later, maybe probably I'll do it next time to not overwhelm you today with information. But yeah, probably just do this next time. But the trick for now is just to, instead of like computing this up to pi over 2, let's compute this up to t. Okay. Then let's say t is somewhere in here. Maybe t is in here. So instead, what we're working with is that the area function, which is the integral from 0 to t of cosine of x dx. So it is the same as before. It's just that the where the integral finishes, before it was finishing at pi over 2, now it's just finishing at a variable that I'm calling t. The advantage of doing that is that now we can use the fundamental theorem of calculus, because now this is a function of t, because you're allowed to vary the endpoint. And so the derivative of this with respect to t, so this is like, again, by the fundamental theorem, is just according to the fundamental theorem, it is take the function you started with and just replace the variable with t. So the function you started with becomes, it was cosine of x, and it becomes now cosine of t. Is that making sense? So far, so good. But now you ask the same question. Now we're trying to find a function whose derivative gives you cosine of t. So of all the functions that we have seen in the past, was there a function whose derivative gave you cosine? Which one was it? What function had as derivative cosine? Which function that we have seen had its derivative equal to a cosine? The sine, good, perfect, excellent. So this area function should be sine of t, and that one, that seems reasonable, plus a constant, because of the same thing that I was saying before, like this is like a constant, because that still has the same derivative as sine, right? Because the derivative of sine plus constant is cosine. Okay, so that means that a of t, which was the integral from 0 to t of cosine of x dx, is actually sine of t plus a constant. Okay, but again, so far so good. So I'm saying that now we have narrowed down the list of candidates tremendously, because instead of like being the integral from, you know, instead of being like some random thing, we just know that this has to be sine of t plus something. Okay, so now we have like pinned down very well like what like we are almost there. Now what you can say, as like before, is that a of 0, right? If you plug in 0 here, right? And again, for the same reason, because this is going from 0 to 0, this gives you it gives you 0, and then you get 0 plus c. Okay, so that means that the constant had to be 0. And so a of t equals the integral from 0 to t, cosine of x dx equals sine of t. Is that okay? Is that making sense? Are there any questions up to this point? So what if you plug in a of pi over 2? That would be the integral from 0 to pi over 2 of cosine of x dx. So that would be the sine of pi over 2. And what the sine of pi over 2? That's 1. So that means that the area that we were after is just 1. The original area. Oh, is that what I was, that's what I was arguing, that, in principle, it was plus c, right? There was a plus c at the beginning, but if you evaluate it at 0, you get 0 here, right? And sine of 0 is 0. So you can actually realize that the value for the constant had to be 0. Is that making sense? So that's what the value for this integral would be. And now comes the most, maybe, I don't know if you start seeing a pattern. So like maybe there's like a natural question you could be asking yourself. I mean, not sure if anyone is thinking about this, but what could be a thing you're wondering about this right now in those two examples that I have done? Well, what you see here is that the two examples that I did, what were two examples where the constant was always 0. You could ask, is that what you would expect in general, right? So the question is like, will this always be happening? And the idea is no. So let's do an example before the quiz. This is the last example before the quiz, and then next time after the exam, on Tuesday, I'll restart this. Like I'll tell you like the actual process, like in a more like a complete way. But just to finish today, let's do another example where you see that the constant is not 0. So something easy. Let's say I give you I gave you y equals e to the x, and we want to find the integral from 0 to 3. Oops. So let's say I wanted to find the value for this integral. So I want to find the area from 0 to 3 of e to the x dx. Okay, I want to find this. And again, in this Well, let me put it with something. Maybe I shouldn't put it to the end. Should I put something else? Because otherwise it would be confusing. What something? Well, let's do it. Okay, do I know? Okay, let's do it with. Um, Otherwise, I think there would be. If I do this example, it would be slightly misleading, which I don't want to. Um, so let me put. Let's do the sister of the previous one, which is with sine. So here's kind of like sine of x. I mean, yeah. So maybe here's y is equals sine of x, and I want to do. I'll do the integral from 0 to pi over 4. Find the integral from 0 to pi over 4 of sine of x dx. Yeah, I think this will be better. So again, we kind of instead of working with this directly, we kind of do it in the general case first. In the general case, we have the area function. And now the fundamental theorem of calculus says that the derivative of the area function would be the function inside. The function inside is just sine, but you have to write it in terms of t. So the function is the derivative would be sine of t. So now it's the same. We are asking for a function whose derivative is sine. So anyone remembers a function whose derivative is sine? What could that function be? What has derivative sign of the functions we have seen? Good, mine, excellent. You're getting like now you're starting to think about how to find integrals. Yeah, that's good. And because of the same, like there could be a constant here, because if you add a constant to this, it still gives you the the value. So what that means is that the area function has to be, which again it was this, but it also must agree with minus cosine of t plus t. Okay. And if you do the same trick as before, which is a of 0 as the integral from 0 to 0 of sine of x dx, well, that always continues to be 0, but now that gives you minus cosine of 0 plus c. Okay. Is that making sense? So what does that give you? Cosine of 0 is not, you know, that's not 0. So that gives you 0 equals minus cosine of 0 plus c. So that gives you the value for the constant, which is cosine of 0. I mean, that's also 1, but it's more convenient to leave it as cosine of 0 so that you see what's about to happen. Is that making sense? So this is just an example where this constant c is not 1, it's not 0. That's what I wanted to find here. So that means that the area function was a of t equals 0 to t sine of x dx, which is well, let's write it as that, minus cosine of t plus c, but c is 1. Okay, so if you wanted the integral from 0 to pi over 4, you evaluate this at pi over 4, so it gives you the integral from 0 to pi over 4 of sine of x dx, and that's minus cosine of pi over 4 plus 1, and that's, well, minus root of 2 over 2 plus 1, whatever that is. Okay, is that making sense? But this is an example where you see this constant of integration is not that's how it's called, the constant of integration. I should say that this constant is not 0, and so what I'll do after, again, because on Monday you'll have the exam. So what I'll do on Tuesday, once we come back from back again this topic, I'll tell you more like the precise algorithm. So like the algorithm consists in finding what's called an antiderivative, which is a function whose derivative is the one that you were integrating, and you just evaluate the antiderivative at the endpoints of. So I'll kind of summarize, redo this for you next time on Tuesday in a way that's kind of more like mechanical. So it will be a little bit easier, but it's kind of nice to do it like from scratch at the beginning to kind of get like an idea of what the pattern is looking at. If you look at what all these examples had in common, is that we were trying to find like a function with a specific derivative. We were trying to find a function with specific derivative, and that's called the antiderivative. And that's what I'll explain to you next time. Are there any questions before we proceed to the quiz? Is that okay? Okay, let's see. Let me go to Firefox. Okay, so I'm going to, as usual, going to make available the quiz right now, as well the upload. So yeah, you can start taking it if you want. And I'll send you again the information about the exam and the study guide and the practice exams later today. So you can keep an eye on that if you want as well. You too, you too.